going to take a look at this problem called count submatrices with all ones. So the problem says we get a matrix with n by m dimensions, so it's not a square matrix, and the matrix contains only 0 and 1 values. And we want to count the number of submatrices that have all ones, only ones, that don't have zeros. And so as a first example here, if we take this matrix here, what are the number of submatrices that have value 1? Well, we have 1, 2, like the one element is considered a submatrix, and then it has size 1, but we should count it. So just for this example here, we have 1, 2, 3, 4, 5. So we have 5 1 by 1 matrices, submatrices, right? And then we can see here we have 2 dimensions. So for 2 or 1 by 2, actually it's 2 by 1. So if we consider 2 to be horizontal, if we consider 1 by 2 to consider the this one here is the vertical dimension. So we have 2 here, we have this and this, the one before it, so that's 2 at least, and then we have third one here, so we have 3 1 by 2 matrices, and then we have submatrix, and then we have this one and then this one, so that's 2 of them, so 2 of 2 by 1. And then we have, what else? We have 3 by 1 by 3, right? So 1 by 3 submatrices, and we have only one of that one. And what else do we have? We have, we have this square here, 2 by 2. So 1 2 by 2 as well. Submatrix is there anything else that we didn't count? Let's see. So this overall gives us 5 plus 3, 8, 10, 11, 12, but there are actually 13, so we probably are missing something. So 1, 2, 3, 4, 5, 6. Actually, there are 6 1 by 1. And so it's 13. That's the result we should return here. So the problem again is we get a matrix, we want to find the number of submatrices that have all values of 1s, submatrices of size just one element should be counted. So that's the problem. Now let's see how we can. Okay, so how can we solve this problem? So the first thing we can think of is, okay, if we are going to solve it with brute force, how can we do that, right? Okay, cool. So one thing we can do here, let's just first take the example matrix that we had there, which was m equal to, so this was example 1. It was 1 0 1 1 1 0 1 1 0, right? Okay, so with this one, what we can do is just fix the top left corner, right? Fix each element, so brute force by fixing each element. Each cell as top left corner, right? Of a submatrix, right? Or as a top left, and then count all. Then after that, what we do is count all submatrices that have that cell as their top left, that have that cell as their top left. And since it will uniquely kind of identify it, we won't count multiple times. For example, here what we will be doing is, well, we will fix 0 0 as top left, and then with a function we could go and say, okay, well, we could construct, for example, we could say, well, we could construct this here, right, the cell itself, and then after that we could construct with this 0 0 as top left, that one, and then after that we can say, okay, we can also construct this whole thing, and then we will be done. But why we are done? Because we encountered 0, right? Right. So one thing we can say here, when we encounter 0, this is of course when counting the submatrices, break or skip or whatever we want, right? So that's the main idea of what we are going to try here. Now you can see here what I did just manually here is I fixed 0, 0, and then I tried all the columns that tried going down through the columns so that I can construct a submatrices. As long as I have one, I keep going down, down, down with the I keep increasing the value of my row, right? And I do the same thing for the column. I go check if I can increase. I can't because there is 0, but if there is 1, if I had like 1, 1, 0, well, for something that starts like this, I would check here because that's a submatrix that starts with that one. And then if there is a 1 here, I could extend, but since it's 0, I stop, right? So when we encounter a 0, we need to stop. Okay, so what this tells me is, well, I will need the first for loop, right? So just to outline my algorithm here, I will need first a for loop for each cell as top left, right? And so to do this one here, I could do it with 2 loops, right? One loop is, let's do it in a for loop. So it would be for, if the number of rows is rows and the number of columns is in a variable called columns, then I would do for row in range of rows, right? And then I would do for C in range of columns. And then I would have a general counter here, right? And then for that counter, I would just create a helper function that will give me all the submatrices that start at that top left. And I will pass to it this one as the top left corner. And then at the end, I could just return my count. And now, what my definition here is that helper basically counts the number of submatrices that have RC as top left. So pretty much, right? Okay, so now how can I define my helper function here, right? So this is going to be algorithm of a helper, right? So the helper function here, I will need it to go through all the rows, each row starting from the row of the top left. And then for each one of them, check all the columns, right? Because we want to try all of these, we want to try all of these. And every time when we reach 0, we should stop, right? So what this would mean here is loop through row in A, so this would be AB, to the length of rows. So basically, if I may, let's say if I had 1 0 1 1 0 1 1 1 0, maybe something like that, and then maybe I don't know, maybe 1 0 1 0 1 0 1, right? Something like this. If I had my if I'm in my processing of every cell, I'm here considering this as the top left, then I would need to go consider here, but that's 0, consider here, but that's 0, but I would need to check them, right? And so this my loop will need to go to the next row, but for each row it needs to go to each column starting from its own row. So I will need to here loop through column in B, of course, right? Because B is the column that we are at here, so we are not going to check here, right? Because that's not the, so we'll start only from B and go down. Sorry, from B and go right. So we'll just be doing this direction here. right? So in B, 2 columns, right? Okay, so after that, when I find 0, I need to break or stop, right? Because I can't, if there is like if I had 1 here, let's say maybe we had something like this, an additional row, I can't do a submatrix like this because there is a 0. So once I encounter a 0, I need to just stop processing the columns here, right? So to do that, I could just check here, well, if the matrix at, let's call these maybe I and j. At I and j, if that is equal to 1, then I'm good. I need to increase the count because my size increased, right? So I need to increase the count. So I need a count here equal to 0. So here I can increase my count. But if it's equal to 0, that means I need to stop or exit. But stop, I need to exit just the columns loop because I need to go to the next row and check it. If I find 0 here, I shouldn't not check the second row. I should go and check the second row. So I need just to exit this loop here. So a way to do that, I can change this loop a little bit and have j still starts from B, but stop when j is no longer less than bounds, and defined my bounds initially to be columns, right? And then here, when I find 0, I can just say or maybe let's call this column bound or something like that to make it column bound. And then here, let's call it column bound. So here, when I find 0, I need to make this equal to j, so that this condition here becomes false and I exit the while loop, right? So this is one trick we can do to do that. And then at the end, I could just return count. You might be wondering why I've done count plus 1 here. Well, if we have, let's say 1, 1, and let's say we examined here, we added 1, and then we examined here. What does this one add? Well, it adds itself, definitely. So that's 2, right? And then when we encounter this one, we need to add 3 as well, right? And so that's pretty much it for this function. We just need to put these two algorithms together. We go through every cell at the top left, and then for each cell we check how many submatrices we can get that have it as a top left. Okay, so let's start writing this. So let's call this count submatrices. And we would have M here, and then we need to start basically doing the algorithm we mentioned here, right, for each cell as the top left. So there we need, of course, to have let me first give some space here for the helper function. So my helper function is going to take A, maybe, and B, let's call, or R and C as the top left corner, right? And then let's give it some space, and let's do that here. So here, the definition of our going through every cell here. So let's just define rows as the length of the matrix and columns as the length of the first row. And now we can say the count that we are going to use here equal to 0. And now we can do the for loop that we want for each cell to be the top left. So for R in the range of rows, and then for C in the range of columns. we are going to say count we will tell the helper function to go count the submatrices for us, so that have the top left as RC, and then at the end we need to return count. Okay, so now we need to define the helper function, and so for the helper function what we need is so the first thing we need is we need to define the column bound here that we just said in the algorithm earlier. It starts out as the columns, right? That's what we said here. So it's the same as this, but we need to write it in a more like Python. And so here we need to loop through the rows. And so to do that, let's take this. So for I in range of rows, but it starts from the top left always, right? And then, well, we need to say what is j. So j in our case here is, it starts out with, as we said here, with b, right? Because the top left is, sorry, it starts with c because the top left corner is RC, so this is c here. And then our while loop for the columns is while we are still in the bound. So call bounds, right? Which initially is just the number of columns, the length. Okay, now we check if the element is equal to 1. That means we can count it. And so we need to define a count variable here, which starts out as 0. And so if this is the case, we can add 1. Then, if that's not the case, then we encountered 0, we need to exit this while loop, and so to make that happen, we can just say that that column bound is equal to j, so that this while loop condition would be false, and we'll exit. And at the end, once we are done, we can just return count. And that's pretty much it. So go through every cell, consider the top left. For each top left, calculate how many submatrices we can find of all ones that start at that position. And that would be pretty much it. Now let's see how the time complexity for this solution. So we can see here we have this for loop, which is if we consider rows to be n, then this is O of n. This is O of m if we consider the columns to be m. And then the helper function here, this is as well O of n at most. This is as well O of m at most. So you can see it's nested, so it's O of n. So overall we have O of n squared by m squared time, right? In terms of space here, we are using these variables, but nothing really, yeah, no extra space here, so it's O of 1 space. So it's still like not like O of n, m or something linear, but it should be efficient enough. So let's run this on some examples and just make sure it works, and then we can see another solution. Okay, so I just wrote down the solution we just saw in the overview, and let's take a look. So first of all, we need to just do some setup for variables, and then for every cell we take a look. We consider it to be the top left, and we call this helper function to get us the number of submatrices starting at these coordinates as the top left. And then we have this bound for j that is initially set to the number of columns, right? And then we just go through the rows after, like the top left corner, and the columns after the top left corner's column, right? We could also make this just be named R and C, right? And then if we encounter 1, we just add to the count. Otherwise, we set the bound to be g so that we can exit this while loop, because there is no need to pursue further to the right columns if we already found 0 in between, right? And so we just go to the next row and check again there, and we keep going until we reach the end or found zeros on both the row, for every row essentially. For every row after the top left corners row, of course. And that's pretty much it. So I have here some examples that we can run this on. Not exhaustive, of course, but I have the asserts for the right value. And if we don't get any assertion errors, that means this passes. So we didn't get any assertions errors, so this should be good. Okay, so next, let's see if we can solve it differently than this solution. Okay, so let's see how we can solve this problem using a different solution. So the main idea behind this solution is the following. If we have a matrix, right? So let's just represent it like this, right? Or maybe this way. Now, if we have a way to obtain for each submatrix, let's say like this, to obtain the total sum of the interior area, then we can check if that sum is equal to the size of the elements in that matrix, in that submatrices. If it is, then that means it contains only ones, which means we should count it, right? So the idea here is we need a quick way to calculate the interior sum of a submatrix, right? Let's say, for example, with this one, let's call it maybe let's call it B, right? So if we have a way to find the sum of B quickly, then we can just check if the sum or if interior of B, right? If interior of B is equal to the number of elements in B, then we can conclude that B contains only ones, right? At that point, that means that count plus 1, right? We can increase the count, right? And so this is the main idea here. Now, how can we find a way to quickly calculate the sum of a submatrix? We can just use the idea of prefix sums, right? But just on matrices, right? Because in the same way that if we have an array like this, let's say we have 1, 2, 5, 7, something like that, maybe 8, 11. To find the sum, for example, of this area here, we just need the prefix sum to have the prefix sums like this. 7, that would mean 15, and then 8, that would mean 23, and then here that would mean 34, right? So to find the sum of this area, we just take 23 minus 3, right? Which will give us 20, and 8 plus 7, that's 15, plus 5, that's 20, so that's correct. So we just need to take this minus this, right? And so in the same way, this can be scaled up to a 2-dimension array or a matrix by doing the same thing, but except a similar thing, but except the calculations rules are a little bit different. So let's see. So this means here that if we compute the prefix sum, then we can easily find this sum and just check the size, right? What is the size? So the size here, or the number of elements in B, if we have a submatrix like this, right, with R1, R2, R1, C1 as the top, if we have R1, if we have R1, C1 here as the top left, and then we have R2, C2 as the bottom right, then the number of elements is just the sum here, which is R2 minus R1, right? Plus 1, that gives us the multiplied by, that gives us the row's dimension multiplied by the column's dimensions, which is just C2 minus C1 plus 1. So this gives us the number of elements. And so now all we need to do is find how to pre-compute the prefix and how to find quickly the sum of the interior area using that two-dimensional array that we will have calculated, right? Okay, so let's see how we can do the calculation for the prefix sum. So one idea here is that for the prefix sum, if we have a matrix like this, and we want to calculate, let's say we are at this position, and we want to calculate its prefix sum. Well, its prefix sum is this area here, right? That's the prefix sum, because the prefix sum is starting from the top left corner to that element, right? So if we look at that, then it's just this portion, right? Plus, of course, here, this goes here, plus this portion here, right? The portion to the bottom, sorry, the portion to the bottom, not like that. Okay, plus this portion here, the entire portion here. But then the problem is that this inner area here, we counted it 2 times. So we need to subtract it once to make up for that. And then the other thing to add is the element itself, right? Okay, so again, if I have a matrix like this and I want to find this area here, then it's just this, right? Plus this area. I meant here, this area, sorry. Plus this area, minus this area here because we counted it twice, plus this here, right? So this is how we will calculate the prefix sum for a position. So let's give these dimensions. So this here, let's say this one here is R2C2, right? Or actually, let's just call it, RC, right? That would be better. So let's say the prefix sum is, we are going to put the prefix sum in a DP array called DP. It can be called prefix sum, I'm just going to call it DP here. So what would be DP of RC here? Which would be just the sum, the prefix sum at position RC. So we will need this area, right? What is the coordinate here? This area is just the prefix sum for this coordinate at this position, right? And so what would be that position? So it has the same column, but it has row -1 because there is this cell here that we are just adding. So this here is just the same column, but R -1. All right. What about the other one? The other one is here. So this one is a prefix sum, but for this position, right? For this position here. So it's the same column. Is it the same column though? So this is the column, and this is the row. So it's the same row, but not the same column. It's just -1, the same column -1, so RC -1. Okay, so that would mean here we have DP of R -1C plus DP of R C -1. And then we need to subtract the area here in green because we counted it twice, once for R1 minus R -1C and once for RC -1. So we need to subtract. What's this area, this green area here? Well, it's just the prefix sum at this position, right? And that position is here and here. So it has the same, it has the column just to the left of C, so it's C -1. But what is the row there? So it's C -1 here. It has the R minus 1, right? Because it's just the row below, above here, the row above R, right? So it's R minus 1. And then we will need to add the element itself, this here, right? And so that would be plus the matrix position RC. So this is the way we can compute the prefix sum at the position RC. But just for the sake of these C minus 1 for when C and R minus 1, when C is equal to 0 and R equal to 0, these would be not correct values. We are just going to pad the DP array indices by 1. And so what that would mean here is that, to translate it here, we are just going to say that this position is going to be just R plus 1, right? So that would mean this won't change the value, so it should be fine. DPRC plus DP of, sorry, here. So R minus 1, that means just it's one position before before R plus 1, so that's just R. C is the same position as here, so it should be C plus 1. Here, the same position as as the row that we had, so R plus 1. And then C minus DP of R, C plus M of. We are going to keep the matrix dimensions as RC because the padding is going to be applied only to DP. This technique, this here with the padding of +1 is good to know. So we just get used. You should just get used to using these dimensions. So now that we have the formula for the prefix sum, the way to calculate it is just to do a for loop. So just do a for loop for R in the range of the length of rows, and then another for loop for columns, and then just plug this formula in, right, to count the prefix sum. And this would be the prefix sum calculations. And then after that, we will need to do the interior calculation, and from the interior calculations, we can compare it against the number of elements and see if they are equal. So how to calculate the interior? So this is, again, the same way we describe the one-dimensional array solution. So if we have a matrix like this, and we want to calculate the prefix, the sum of this area, right? So the sum of that area is just take the prefix sum at this position, right? Position here, and then subtract this area here, right? Which is the prefix sum at this position. So we want to write it in terms of prefix sums because we have those values, and we can do like a formula calculation on them in all one time. And then we have the prefix sum of this area at this position. And now you can see that we counted this area here 2 times, right? So it's the green here minus the red one minus this this one here, and then we would have subtracted the yellow area twice, and so we'll need to add it once, and that will leave us with the content of this, right? So if let's use this position in the padded dimensions here, +1 here. So what this would mean is that this is R plus 1, C plus 1. So what does this mean? This means that the formula we are looking for is the interior area here of that square. Then we need to so actually let's say this is R2C2, and this here it's top left here is going to be, let's say, R1 plus 1 C1, right? C plus 1. So to clarify, the interior we are looking for is for an area like this, where here it's R2 plus 1, C2 plus 1, and here it's R1 plus 1, C1 plus 1, right? And then we are looking for that area, right? So what is the interior here? So it's the green area, which means it's just dp of R2 plus 1, C2 plus 1, right? So it's just the dp of, so it's just the prefix sum of this area here, which we already calculated it. Now minus this area here, right? So this area is the prefix sum at this position. What is this position? So that position has the same column as R1 plus 1, C1 plus 1, and has the same row as R2 plus 1, C2 plus 1 dimension. So what that would mean is that we need to subtract, has the same column as the R1 plus 1, C1 plus 1, so it has, so first let's see the row. The row is this one here, it's R2 plus 1. Not R2 plus 1, sorry, I need that. Yep, it's R2 plus 1 here, so, and what is the column? The column is here, so that's C1. Because let's actually just say that this instead of, it would be easier if we make this just be R1 C1. Then we need to subtract, so that's why we have C1 here, and then we need to subtract this area here, right, which has this position for the prefix sum. So that position has this as the column and this as the row. So that would mean we have dp at position the same, the row is just R2 plus 1 minus 1 because of this cell is just dimension 1. This cell dimension is actually the same as this one, the same as R1 C1, the same here. It's this row, so it's just R1, right? And the column here is this column here, which is the same as C2 plus 1. So let's say C2 plus 1 here. And now we need to subtract this green area here, which is just the prefix sum at this position. What is the prefix sum at that position? That's here and here. So the same row as R1 C1. So let's add it again. We are adding it again because we subtracted 2 times here and here. So that would mean here we need to say dp of R1, and the column is the same as C1, right? So dp R1 C1, right? And then from there we have the submatrix here, and we have its sum, and so we can compare that against the number of elements. Yeah, so that's pretty much all we need, right? We know how to compute the prefix sum. We have the interior. We know how to compute the interior area quickly. This would be all fun operation, and then we know that if it's equal to the number of elements, that means it's a submatrix of all ones. So we should count it, right? So let's do this then. Let's write this down. So count submatrices here, and the matrix is M. And the first thing is computing the prefix sums. So that would mean here that we first need to initialize our dp array here, and then first we just need the dimensions. So rows, columns is equal to the length of M and the length of M0. And then we will need the dp array here, which is dp of 0 for a range of rows, a range of columns here plus 1, right? Because these are the columns dimension, and then sorry. This will repeat for range of rows +1. We are doing +1 here to account for the dimensions of +1 that we are using here. Now let's start the calculation for the prefix sum. So for R in range of rows, and then for C in range of columns, let's plug in the formula for our so we could just take this, move it here, sorry, there. So it's just using this formula here. Sorry, I'm just trying to get this to align correctly. Cool. Okay. Okay, so this is the formula for the prefix sum. We plugged it in. The next step is to start the interior calculations for every possible area in the matrix, right? And so to do that, first we need to go through the top left corners. So for R1 in range of rows, and for C1 in range of columns. So this is going through the top left corners. So top left. And then we need to do the bottom right, right? So the bottom rights are 2 here. But the bottom right has to be after the top left, right? So that would mean here we need to have R1 here up until rows, and the column, same thing, has to be to the right of C1. And this is the bottom right. And now we can take the formula that we created earlier for the interior and just, sorry. Sorry about that. Cool. Okay. So here we have dp of R1 and C1, right? That's the area we removed. That's this area here, R1, C1, this area. Okay, so now that we have the interior, we can just check. We need first to have a count variable here that we can increase. So count equal to 0. And then here we check. So we do the check here if interior is equal to the number of elements, and the number of elements is just, as we said earlier, it's R2 minus R1 plus 1 multiplied by C2, or let's just do like this differently. So the bottom left we said is plus R2 plus 1 minus R1 multiplied by the bottom right, which is C2 plus 1 minus C1. And so that is the size. And then here, if that's equal, that means the submatrix contains only ones, so we can increase the count by 1. And then at the end, once we are done, here in the for loop, after the for loop, we can just return count. and we will be done at that point. Okay, so that's pretty much it for this solution. If you want to take a look at the time complexity here, we could see that here we have O of n, if n is the number of rows, O of m, if m is the number of columns. So that's a separate, just the prefix sum calculation is O of m, n plus m, right? Now here we are doing an O of n for the, and O of m for the top left corner loop, and this similar one for the bottom right. And so overall this here is O of n plus m squared, right? So n by m, so that would mean this here is n squared and then m squared, right? And this is bigger than the O of n plus m, so this overall is just O of n squared m squared time. So it's definitely not that efficient. It could be improved, but it's a good solution to know. Okay, so now let's just test this solution on some examples and make sure it works. The solution that we just saw in the overview. So the first step is to compute the prefix sum, right? So we just need the length first and then initialize the DP array. And then after that, we need to compute the prefix sum. So we go through every row and column cell. And then we compute for each one of them the prefix sum with this +1 for the padding, just to handle the case of C-1 correctly. And then after that, so this is the same formula that we came up with in the prefix sum calculations. And then after that, we want to calculate the sum over every submatrix in the matrix, right? So we go through for every top left corner and then every bottom left corner. We compute the interior and check if the interior is equal to the number of elements in the submatrix. If it is, that means it contains only ones, because if there was a 0, then there would be a difference, because here the interior counts every element, like counts it as 1, but here if we are missing one of them because here counts every element's value, but here we count only their number regardless of the value, right? So if these are equal, that means we have only ones, but if they are not equal, that means there is at least a 0, which means the submatrix doesn't contain only ones. And so only if it does, we increase the count, and at the end we return the count. Okay, so now I just replaced the calls here to call this function instead of the one we had before. And so the test cases here, the assertions of test cases here should pass fine, and they do. Yeah, so that's it for this solution. Okay, so now let's try to come up with the solution better than this one here, the of n to the power of 4. If we consider n and m almost close to each other, it's O of n squared by m squared. So let's try to improve that solution. So the main idea behind that solution is this. Let's say we have a matrix that is maybe 0, 1, 1, 0, 1, 0, 1, 0, and then 0, 1, 1, 0, 0, 1, 0, 1, something like this. So the idea there is that if we do something like run length encoding, which is basically we will gather, it's similar to run length encoding, but it's not exactly that. So let's say if we have an array like this, we would gather until we reach 0. We would add the elements together until we reach 0, then we reinitialize to 0. So for example, here we have 1 and then 2, and then we encounter 0, so we put 0 here, and then we have 1, and then we have 0, right? And so you can see here when we kept summing up, but when we reach 0, we initialize. To take another example let's take another example to make this super clear. So if we had, let's say 0, 1, 1, 1, 0, 1, 1, 0, maybe 1, 1, 0, then that would be 0, 1, 2, 3, 0, 1, 2, 0, 1, 2, 3, 0, right? So it would be something like this. But we'll do it for each row in the matrix. So with that, in our matrix here, that becomes 0, 1, 2, 0, 1, 0, 1, 0, 0, 1, 2, 0. Let's adjust the matrix here a little bit so that this becomes more interesting. So we had 1 here, so that would be 0 here as well, and then 1, 2, 3. Okay, and so then what we are going to do is consider each, this is the key idea here, is to consider each cell as the top right, not the top left, which is what we usually do, but consider it to be the top right, and then iterate down and consider each element down on the column as a bottom right, and from there see how many submatrices we can construct going to the right. What this would mean is that, let's write this down just so that it can be clear. So consider each cell as the top right corner of matrix, of submatrix, and then each row is cell that it has a value different than 0, or the value, yeah, different than 0 in this matrix, the errorified version, right? And then after that, go down on the same column and consider each cell. So this would be maybe R1C as the bottom right. And so the row would be different, but it would be the same column. So let's say, so this would be R2C, right? And now, so what that would be like is, let's say we start here as this is the top left. And so we'll go down, so this is 2. So let's say this is our top left here. So if this is our top left, then, well, we will go down and try this as the top right. So, and what do? We pick the min of the value, because if you take a look here, well, we have this, once we have this as, if we take just the first element as the top right and the bottom, then it's just 1. But if we go down and consider this the bottom right, then we have, well, what are the submatrices we can do to the left? Here we can do only this, right? We can't do this here, we can't do, because there is a 0. So it's just the min of this one and this one. It's the min of both, right? Now if we go even down further, let's say we go here. So we are, at this point, we are down here. Then we can, 2 here tells us, the min of 2 and 2 tells us that we can do 2 additional submatrices going here. And that's correct, because we could do the one here and we could do the one here as well, right? And so what this would mean here is that we will take the min of the matrix and R1 here, and for the matrix at R2C, and that would be, and we will add that to the count. That would be how many, this would be the number of rectangles, of submatrices, or submatrices, that's the same, that we can do with R1C as the top right and R2C as the bottom right, right? So if we are taking this 2 here as the top left, top right, and the 2 below as the bottom right, then well, what we can do, not this case. This case is only if we are taking 1 as the top right and the bottom right. But if we are taking this as the top right and this as the bottom right, so we can make 2, because we can make this one, right? And then what else can we do? So we have 0, 1, 2, 1, 0, 1, 0, 0, 1, 2, and then this one here, right? Okay, so this is the main idea here behind the solution, is to pick 1 as the top right, and then iterate down considering each cell on the same column as the bottom right, and then the min, that's how many additional squares we have. And that's pretty much it. So let's write this down. So the first part would be to realify this matrix here. And so let's write this down. Def count submatrices. So okay, so the first thing is realifying here, but we need couple of setups. So we need the rows, which is the length of matrix, and then we need the columns, which is the length of the first row, and then we need the DP array where we'll put the reified version. So that would be 0 in the range of columns, or actually we don't need DP because we can just do it on the matrix itself. We can just modify the matrix itself. So let's not do that. Let's just go here and start the for loop here to go for every cell and every column. So this would be range of rows, and then this would be range of columns, and then after that, well, only if the value is 0, then we need to leave 0, right? Like here, if the value is not 0, then we will need to do to add to the previous one, right? So here, if is equal to 1, right, and the column is bigger than 0, right? Because if it's equal to 0, then that means it's the first one, so no need to do any operation. Then what we want to do here is, well, we want to just do the adding here, which means this is going to be plus the previous column's element, right? Okay. Now we have the realfied version. We'll start to do the operation here where we consider each cell as the top right, go down to consider as the bottom right, and then do the min and add that to the count. So we need the first to initialize our count. So let's initialize our count to 0. And then we'll do the for loop here. So we need 2 for loops. R1, right? Considering each cell as the top left. And then for C in range of columns. And so at this point here, we would have R1C top left, okay, and then we will say that we need to take the min, right? And so here we will do also a for loop here but we need to go the min all the way going down, which means here the min between these, that's 1, right? That's between 2, 1, and 2, which is correct because we have only this one. We don't have another one that has the same top and the same left. So we need to take the min all the way going down. So we need to initialize it first. So let's call it M. It's going to start off as R1C. And then we are going to say, let me just iterate again, because maybe I didn't clarify that later. So if we take this as the top right, then we go down. This is the bottom right, so the min now is equal to 1, right? And that's correct because, and so we add only one square, we add only one submatrices, which is this one. And then we will go down again, and we are here. We have 2, the min right now is 1, and so when we compare it with 1, it's with 2, it stays 1. And so we can only make one submatrices. And that's correct because the only submatrices we can make that has this as the bottom right and this as the top right is this one here, right? Okay, this one is different. This one here is different because this one here has this as the top right and this as the bottom right. It's not the same definition, right? So that means here that we will initialize to m first, and then we will do another for loop, right? So we'll do another for loop that for the to go down on the same column, and so we have R2 in range of, but it has to have the same. It has to have to be below the, because below the top right, right? The bottom right has to be below the top right, so it has to start from R1. And then we take the min as we go down, so the min between the previous min and R2, see the value we have right now. And once we have that, we need to add to the count, right? So this would mean here that count increases by that min, right? Because that tells us how many rectangles, how many submatrices we can do with that top right and that bottom right. And then at the end, once we've done all this processing, we can just return count. So here we return count. And that way we are done, sorry. So yeah, first part here, this is the RLFI kind of. And then this version here, this is the calculations. Now, if we take a look at the time complexity here, we are doing of n of m here. So overall here, it's of n m. Time here, we are doing of n. Here of m. And here we are doing another of n. So overall, this is kind of, this is of n m, this is of n squared m, so this is bigger. And so overall, we have time complexity of n squared m, right? So it's kind of a cubic solution. And yeah, so it's better than the previous one, which was m squared. Okay, so now let's write this down and run it on some examples, make sure it works. Yeah. Okay, so I have here the solution that we just saw in the overview. So we go through the matrix and construct the RLA version of it that we mentioned, where we add numbers together, and then when we encounter zero, it becomes a 0. And then after that, we count the submatrices using what we mentioned, where we take the top right and the bottom right. We fix the top right, which is using these two, so we can maybe rename this to C. And then this one, we pick this one as the initial value of the minimum. And then we go down and consider each cell down in the same column as the bottom right. And then once we consider it as the bottom right, we have the top right and the bottom right. We pick the min, because that's how many submatrices we have, and we continue picking them in as we go down, because if, for example, we have 2, 1, 2, as we saw in the overview, the min should be 1, because if we go all the way from the top right to the bottom right, we can only construct one submatrices and not 2. And then we add that to the count, and that's pretty much it. Okay, so now let's run this on these examples. Okay, so assertions pass fine. Yeah, so that's it pretty much for this problem. It's a little bit tricky on the harder side. but it has a lot of useful tricks, like how to manipulate matrices, how to do like prefix sum on a matrix, how to find the interior, like the sum, the interior sum of submatrices that is like in the middle of the parent matrix. And also it has yep, this clever trick about having fixing the top right and then fixing the bottom right. Usually we fix either the top left and the bottom right. Yep, so that's it for this problem. Thanks for watching, and see you on the next one. Bye.